I think you guys should do that on purpose just to keep YouTube on.
Welcome, lads and ladettes, to Ether Cosmology Roundtable number 105, History of Wave Invariance.
All right, hello everyone. Welcome and thank you. So this presentation has a pretty long title here in the slide, a review of relativistic velocity addition and the transverse Doppler effect, but it ended up turning into so much more. It ended up becoming more about the history of wave invariance. And so we're going to look at the history of velocity addition and then relativistic velocity addition and the different effects that are said to be so-called relativistic. And we're going to look at the history of the ether theories that were put forward pre-relativity that actually use the same exact equations. And we're going to look at the principles in which they were derived under. And we're going to get a real hard look under the hood of relativity and find that the so-called relativistic effects of link contraction and time dilation are misconstrued interpretations of math that describe waves propagating relative to a medium and what a moving observer would see in terms of how that wave would be compressed as a function of velocity with respect to that medium. So we'll get into all the examples there as we continue on. So quick shout out to the homie It's BS on YouTube and it's underscore BS on Twitter. Definitely give him a follow on both of those. He has some very, very high level debunks of relativity. And by high level, I mean, they're very straightforward, but they're high level in the sense that like, they're not refutable. They're not high level in the sense that they're hard to understand. He makes it very, very easy to understand. So shout out to him. Definitely check his channel out. His playlist on relativity and quantum mechanics are fantastic. All right. So here we're going to look at the relativistic effects of gamma are just hiding C plus or minus V. So what they call link contraction and time dilation are just how much faster or slower the speed of light was. And then in terms of representing that mathematically, they've interpreted this as the shortening of the coordinate system rather than the shortening of the frequency or the oscillation rate of a wave. So relativity is just disguising classical physics. But we'll get to all that as we continue over. So starting with the history of light and C, somehow back in 1727, they had the velocity of light and they were using that as a ratio for aberration. So they took the angle, the arctan of the velocity over the speed of light, and that gave them 20 arc seconds. And that 30 kilometers a second happens to match the expected orbital velocity that they would predict if the Earth is in motion following Kepler's laws. So aberration in air, when they line up a telescope to take a zenith measurement of a star, the amount of deviation that they get over the course of a year comes out to be what they would expect for Earth's, as if Earth's velocity is moving around the sun at that expected value. So that was a good agreement for them. And again, that is the V over C relationship. And we'll notice that a couple things to note about the V over C equation is that this is a first order relationship. It's a linear relationship. It's what they would call first order. Now, this will be the only first order measurement that corresponds to the velocity of Earth when there's no medium. And after that, they try to get interferometric measurements and stuff to match, but none of that ends up working out. So they come up and start looking for things at a higher order, but they started here with a first order relationship in V over C. And you can think of this as the speed of light with respect to, it travels at this speed with respect to its own inertial frame. And that would be you could consider that absolute space. So that's what this equation implies. It's an absolute velocity. It's a ratio against light in its inertial frame, which would be the ether frame. It's a it carries a certain mathematical implication with it, right? Like it's not just a ratio of a number; it also has an implication attached to it based on how it was derived and how it's used. So continuing the aberration measurements, a guy named Arago in 1806 and 1810 conducted some measurements of his own where he introduced a half-covered telescope with a crystal prism. And the idea was when the starlight intersected the midpoint of the telescope and it hit that crystal prism, if the Earth is in motion, then the telescope should require a tilt to keep the star in the center. So there should be a deviation when there should be a deviation in the angle when the crystal prism and the starlight intersect. But he never found that effect. He never found that effect. He found that if under the heliocentric paradigm, they would say that the velocity of a moving crystal prism has the same refractive index as a stationary one. That's a direct quote from Whitaker. So that was their interpretation of the results of this. Not that the Earth is stationary and that the starlight already comes in with that drift, so that there's no, or if it comes in with a horizontal drift, then there's not going to be any angle change either. So like that would be the exact dynamic equivalent to what they would have expected if it was in motion. So they just interpret this as, okay, well, maybe there's no way. So this is where they start looking for alternative ways to explain a measurement when they don't get that first order relationship like they did with aberration in air, where the refractive index is very low. So he waited until 1853 to publish these, but he conducted those back in 1806 and 1810. Now, another important feature here is that in 1818, a man named Fresnel derived what's called the Fresnel drag coefficient under the pretense of an elastic ether, and that the ether inside of that matter is proportional to the refractive index squared. So if there's a translucent medium, the amount of ether in that medium that's compacted in there is proportional to the refractive index squared. And with that, he came up with this drag coefficient where if you were to move said medium, the amount of velocity would be transferred to the wavelength of light changed. So in other words, the velocity of the refractive index will change the wavelength of light as a function of the square of the refractive index. And this was again derived under the principles of an elastic ether, which is deriving from which they derive the speed of light off of the same principles that they use to derive the speed of sound through gas. So just density, just that proportional ratio. And they ended up deriving the speed of light, and then using the square of that for refractive indexes. This is what they came up with, and this was in 1818. And then this was experimentally measured a little later on, but we'll get to that as we go down the timeline. I got them kind of going in order. But keep in mind, back in 1818, they were coming up with, how much drag. So like they knew about Snell's law, they knew about they knew about cosines and refractive indexes, and how much angle change there would be based on refractive indexes and whatnot. So as they started to have all these things categorized, we're looking at the basic foundational principles on which they were derived for how they were using the measurements and categorizing them. Like what principles did they derive it under? Well, we're looking at the principles that they were derived under the theory of an elastic medium. So next up, we have Doppler's equations, which describe classic velocity addition, which is just c plus or minus v. And basically, it just describes the relative motion of the source and the receiver, and it describes whether or not you're going to hear blue shift or red shift. So an example of Doppler shift would be, let's just say you're stationary and there's a car coming towards you, and the horn it's blaring its horn. You're going to hear that high pitch, and then as it goes away from you, you're going to hear that low pitch, and that's going to be due to the compression of the waves based off of the velocity of the emitter, and that's all described in these equations here. And he derived these for sound with respect to um, sound waves in a medium. So this is based on the relative motion between the source and the observer through a medium. For sound waves, he started with, and then at the end of his paper, he ends up saying that these also apply to electromagnetic radiation. And keep in mind, this is back in the day when applying classic velocity addition to the speed of light apparently wasn't a violation of their principles, and they all understood the implication of what they were putting forward, and it was no big deal. Because these are the exact same equations that you would use for sound, and when you use them for EM, there's no difference. Nowadays, there's an additional term that's added. There's a gamma term, but we'll get to that as we continue on. And it turns out that the classic theories also predicted the gamma term. Yeah, so we'll look at some examples of some wave fronts here representing Doppler shift. So stationary sound emitter, you can see that the wave fronts all emit out symmetrically. So you can see there's a nice equidistance between all of them. Then when you have the moving emitter, you start to see that they start to get compressed, and it starts to get kind of conical in the formation here. They start to almost overlap. As the velocity increases, you start to outrun the wave fronts that you're emitting. So that's when you break the sound barrier. And then, of course, there's when you go supersonic, and that would be when you're now outrunning the waves that you're emitting. So the wave speed is limited by the medium. Now you're now exceeding that speed limit. And so you're going to travel past an observer before they're going to hear you. Like there's going to be a delay there, and that delay is going to be based on your velocity and the medium and all that. And it's all just described here with classic basic velocity addition with respect to motion relative to a medium. All right. Now, an interesting thing is that this is how police radars work. So military radars and radar guns all operate under the Doppler shift principles. So an interesting thing about velocity and Doppler shift, which we just learned is based on the principles of C plus or minus V, how that wavefront is going to be changed, perceived by the observer. So basically what that means is with respect to the wave moving at a constant velocity, with respect to its medium, the observer is going to see it based off of the factors of, how fast the emitter was moving relative to that medium, and also how fast the observer is moving relative to that medium.
Ooh, question then.
Yes.
What's the equation for something that's sometimes a particle that isn't moving through any medium whatsoever, but is also a wave somehow?
Ooh, fantastic question, dude. That would fall under what's that?
Same
No,
formula?
no. It would they would put it. So this guy. It's funny that you argue that, because this guy who runs this website actually argues. Actually, not this website. The guy that wrote this paper that I'm going to cite here in a second. This late guy, he actually argues that that light is photons, and he uses the equation for Compton scattering, which, if you remember, that was the one that Piezo broke down. You can algebraically shuffle in the mass that they left in, because they don't end with the final reduced form of the formula. They leave it thinking they leave it with like another step that you can do to reduce the unnecessary thing that they interjected in. So it's actually still it's actually still a wave formula in that regard then. But this guy doesn't know that. And because Compton scattering is the most convincing thing, like if you understand the math and wanted to hinge your hat on that, that would be a great place to do it. So he's actually makes that argument that this only works because a Compton scattering photon particle, but sadly that has nothing to do with it. So you would actually just use the same wave equation instead of the photon Compton particle thing, which he does show at the end of his thing that it is equivalent. So great question though.
Now that we've we stopped the flow for a sec. Go back, I think, a slide or two there. One more to the supersonic one there. Is that Lake's graph? And no, that's Wikipedia. Is that their text as well that went with this?
Yep,
graph?
that's Wikipedia's.
That's straight copy. Well, they've kind of bunged it up because if we're talking about supersonic and the Doppler effect with something moving through sound, and and that we're moving faster than the waves, or the sound is propagating through the media. On the right, it should reflect that it's traveling at Mach 1.4, not 1.4 c, which is the speed of light. You know what I mean?
Yeah. So
Supersonic.
yeah. So
It
yeah.
should
So
be
the
luminal, superluminal, or they should change that unit.
yeah. So they mentioned
Discord?
they mentioned no. I don't. I can hear them. Can
Okay.
you? Can they hear
Not that I can
Discord?
hear Stone.
no.
They should be able to. It's showing up on my Discord when they talks. I mean, it's showing up on my OBS.
Oh wow. They can't hear me? That sucks. Oh well.
Shalom says
Point still
you're faint.
stands that
Yeah, but we're
one of
good.
one of the two things should, well, I don't know, maybe
Oh,
Alan
here,
might
here.
have me turn
No, yeah,
down
yeah,
in
yep,
Discord or something.
yep. I turned you up. I had you at 50%.
Aha. Aha. That would explain it. Okay, for those who couldn't hear the first time, we're looking at this. It turns out this is from Wikipedia. When Alan was describing on the left something moving slightly faster than the speed of sound and then becomes supersonic, such that you hear none of it because of how fast things are propagating through the medium, and you've exceeded that by 0.4. Yet on the right in the text, this is a direct copy from Wikipedia's Article 2, as I understand it, they should change that 1.4c to Mach 1.4 if we are to stick with this, what is in the yellow box in the upright in the graph, supersonic. That should be either changed to superluminal or change 1.4c to Mach 1.4 for congruity between these two. Just to point it out.
Yep, and they did
And I hate
mention in
Wikipedia.
yeah, they did mention in the Wikipedia article that C is just whatever wave you're using. So if you're using sound, you would use the speed of
Oh,
sound
wow.
and that, yeah. So they
Wow,
just
that's
made it.
sloppy. But okay. Okay.
Yeah. No,
Fair
no, dude. Yeah, I mean, you are the quality assurance for a reason, dude. But Wikipedia's got you covered.
That's an excellent visual, by the way. These two visuals of it supersonic and then outrunning itself. I don't think I inherently understood what it meant, but to see it like this and to see it outrunning its own self, it was like, oh, that's what that is. That's such a
Oh,
good visual.
okay, dude. Now think about this. When they talk about the muon being confirmed at 16 decimal places or whatever, confirming the amount of time dilation, what we're about to learn is that length contraction and time dilation are just c plus or minus v in disguise. So what that means is the muon move faster than the speed of light. So it traveled a distance further than what would be expected if it was traveling at the hard limit. Well, actually, they say that it travels slightly under the limit. But yeah, so traveling under its imposed speed limit, that they give it, it's like, oh, it can only travel this fast. But all this means is that it's actually traveling superluminal.
That's one thing that Eric Dollard always liked to correct people on who would question him from the audience when he lectures. They would mention C as, that's the speed of light. He says, yeah, it's a constant. It's not a limit. It's a constant.
Yes.
And he smiles at them. And then, oh.
Yeah, that's great rhetoric. No, that's a good way to put it, because we were actually talking to somebody on Friday who was kind of having a hard time with that. And to be fair, like, it is confusing, especially taught in the paradigm now with, C having no association to any physical medium or anything like that. It is kind of hard to grasp the concept of, okay, the light, or the wave rather, is propagating relative to a medium at this constant rate, right? That we're going to use as our constant, but we're going to measure it plus or minus that relative to our velocity or the emitter's velocity.
It's a relative constant. Ah, okay.
Yeah. Yep. All right, cool. So yeah, the principles of radar actually work on this, and there's this thing called a beat frequency. So every velocity in terms of 1 kilometer, 2 kilometers a second, 3 kilometers a second, so on and so forth, all will have their own Doppler shift frequency that corresponds exactly proportional to that velocity. So they have lookup tables. What they can do is once they take the reading for the Doppler reading, once they have that beat frequency, it's always a proportional ratio of the frequency that was output. So if you've ever heard of like the argument, oh, you know how you can get out of a speeding ticket is just ask them, when's the last time your device was calibrated? Doesn't matter at all when the last time it was calibrated. All they need to know is what was the wavelength when it was sent out. And as long as they know that, it's always going to be that beat frequency is always a proportional ratio of that. So it's always going to be accurate no matter what, even if their thing was off, as long as they can see what it was sent out as, then it's always proportional. So that argument doesn't work. But yeah, this guy goes over the math for it. He gives a couple examples here. He uses the most common frequency used for police scanners. He goes over a 70-mile velocity here, and we could see that the beat frequency in terms of hertz. So you can convert it into what it would be as like an oscillation rate. So each velocity has its own oscillation rate in terms of how it retards a wave based or causes it to be accelerated based on actual velocity relative to a medium. So this is all facilitated like mechanistically based off of the velocity being relative to a medium. Now the way that relativity would try and present it is that this is just relative velocity based off of these two observers or whatever, and one being at rest, etc., and then categorizing it and then looking it up later or whatever. But the principles remain the same. And so there's a couple patents here for radar, and it just kind of goes over how they utilize this beat frequency, the way that it's known how the wave is measured, C plus or minus whatever it was sent out as, to make tables and make effective radar guns that can be used while you're moving and whatnot. So like they have ones that send out two beams, one that's like aimed towards the ground, so it returns a stronger signal, and then it determines your velocity based off of that, because once it has the beat frequency for that one, it determines your velocity, and then it subtracts it from the beat frequency from the one that's you're measuring that has the weaker signal, which would be the thing that you're pursuing. So they've they've got it down to a science, C plus or minus V, and just regular technology. It's just the equations that were derived hundreds of years ago under the principles of elastic ether are just still working today just fine. And what they'll say about relativity is that when you're not moving at relativistic speeds, of course, that just means that the relativistic gamma terms fall off and or they're too small to be measured, and that it just falls back to classical physics. But the problem is that classical physics is C plus or minus V. So then they would have to argue that that's somehow an illusion, and the speed of light is really constant for inertial observers, and we're just measuring illusions based off of the constancy of C relative to nothing, which doesn't make sense when you consider a Sagnac interferometer, because you have a physical fringe pattern, and the physical fringe pattern can't be an apparent one. That doesn't make any sense. So as we continue here down the timeline, before we get into Sagnac and the full scope of interferometry, we have 1851. We have Hippolyte Fizeau, otherwise known as Fizzy around here, young Fizzy. Shout out to your boy. So, following the principles of Fresnel drag that were derived in 1818, Fizzy was like, "Hey, I'll invent a way to test this here." So he comes up with an interferometer. This splits a beam of light in a way that completes a circuit, and he has it such that the light path will traverse a tube where he has water running through it, and they know the refractive index of water. They know how fast they can move water through this tube, so they know the rate of the moving refractive index. So we can apply Fresnel's equations, and we can get to the bottom of this c plus or minus v times 1 minus 1 over the refractive index squared, and see if it's true or not. So what he found was when the light beams recombine after they traverse this circuit here, is that they're retarded proportional to the square of the refractive index, and that ends up giving a 44% retardation based off of the velocity of the water, and then it also added 44% velocity addition when it was moving with the water. So that was shown in the fringe patterns when they recombine these over here. What you can do is you can measure the distance between the fringes, and the square of that distance in the wavelengths of which you started with is proportional to the velocity that produced them. So, and then the other way that you could measure it would be if if you had a way to manually measure the wavelengths, you could measure the phase difference that way. But the old interferometric measurements were done by the squaring the proportional distance of the fringe pattern itself, which is equivalent
I know
to...
that you didn't make this diagram.
No, but do you
No,
like
of
it?
course you didn't. You got it out of a book, right? But if anybody ever does want to make another version of this diagram, and in a way that is actually more explanatory of the function, notice how there's yellow coming from the sun, that it's a yellow arrow headed for the first dish, for the BS plate there, the beam splitter. And then as it leaves the other beam splitter next to the eye, it's also yellow. So you're seeing, the yellow sun allegedly traveling through this thing. Well, that's the thing. They should actually change this, that the yellow should continue off the beam splitter in both directions. And when it hits the water where the blue line is, it should change from yellow, from the sun, to red, because this would be arresting the the uh, the the velocity of the light going through, because the water is moving against it, right? It would be arresting the velocity the most out of the two, and that would show us a longer wavelength after it comes out and hits the mirror, and then down to the beam splitter, and then to the eye. On the other one, again, yellow in the vertical where it is currently red, off the mirror, still yellow, and then it hits the water and should turn blue. Because what we're doing here in the water there is this would be technically the faster, the thing that is encouraging the light to move to the right towards the beam splitter, and then would again turn yellow as it leaves the water just before it hits the second beam splitter, and continue yellow to the eye. Does that make sense? Same with the downward
Yeah, it's a
blue
color
arrow
coordinate
on
the
the right. That
velocity
one should also be
change.
yellow. Exactly. And it'll show you
Yeah.
where the effect is happening and which effect is happening correctly, as opposed to the opposite of this completely non-intuitive drawing.
Dang, just when I thought it was slightly intuitive, you made it. Yeah, that would be a good change.
Then it would kind of, make physical sense. Anyways, on with the show.
Yeah, no worries. No worries. Next up, we have a very important experiment here from our boy R.V. Jones using a transversely moving media. So what Fizzy measured back in the 1800s was longitudinal drag. So when the motion is parallel to the light ray. Now, when the medium is perpendicular to that, and it's moving perpendicular to a stationary light source, or to a stationary recorder, what will happen? So relativity predicts that because there's no medium, if you were to set up an experiment where you have, I don't know, a rotating disc perhaps of plastic, the the amount of velocity addition would change with respect to the rotation. So if you're going clockwise, it'll give velocity addition, and if you're going counterclockwise, it'll give retardation. So it should change geometrically with the rotation, because the velocity, the velocity of light and all that is going to be is a function of velocity. So it's going to be measured with respect to which direction this velocity is going. Now, if there's a medium that the measurement is relative to, then then the drag is always going to be positive. It's always going to be positive no matter if this is rotating clockwise or counterclockwise. That's a huge separation here, because if there's no medium for transverse motion, you would not predict the classic, classic theory wouldn't predict any change. So the fact that it changes, and changes always in one direction, we're going to find fully substantiates the position of a medium and the physical interaction of that medium and the light, because otherwise there would be no mechanism to always add velocity addition on that. So in other words, that the motion itself is causing is causing the retardation. So what we're going to see, rather than the geometry of the motion. Okay, so let's see. So yeah, we went over the two effects. So the light coming through and the medium moving transversely. So what Jones came up with here was a rotating plastic disc. We have a source here. It hits two mirrors, gets reflected back up to the detector here. And here we're going to read from his paper. It had been expected that the bifurcance induced by the centrifugal stress might become appreciable, but in practice, this effect was small enough to be neglected at the relatively low angular velocity necessary to give a detectable ether drag. However, even at these speeds, it was found that there was a large displacement of the image of G1 relative to G2, which was in the same direction, irrespective of the sense of rotation of the disk proportional to the square of the rotational speed. So that's pretty profound, because relativity, like I said, predicts the exact opposite. It predicts that it would change with respect to if the disk is going clockwise or counterclockwise. So that's a like the that's irreconcilable. All right, so that experiment was done in the 70s, though, so I kind of skipped ahead, but because it was related to the longitudinal drag, I wanted to include it. And they already kind of knew that there would be transverse effects like that, because there was a guy named Foucault in 1862 who did an experiment with a rotating mirror in a tube filled with water, and what they found was when you rotate a mirror and the light goes through the water, the angle that was observed when the mirror was stationary increases as a ratio of the velocity of the rotation of the mirror. And using different configurations, this produced transverse and longitudinal effects. So they knew about how Snell's law would interact with this, and that's going to be important here when it comes to interpreting the Arago experiment and Airy's failure, so-called, coming up as we continue on down the timeline. Meaning that it wasn't a surprise when meaning that the results should have been a surprise to them, because they expected them to have increased angles if the Earth was the cause of the motion, because they could directly see that same relationship play out in the lab here. Okay, and then in 1864, Maxwell gives his theory, or gives his dynamic theory on electromagnetism based off of a sea of rotating vortices that rotate at the speed of light, and those produce a centrifugal force that carries waves through it at that speed. And using the magnetic and electric constants in a vacuum, the inverse of that gives the speed of light. So he deduced, what you could consider that as if you take all the so-called physical material out of a vacuum, all that's left is the impedance values that dictate the speed of light. And impedance necessitates physicality So as otherwise there would be, the question is, well, what's impeding it? What causes that limit? Well, it's these vacuum constants here, and the inverse of those dictates that constant that they use for their calculations. Now, does it mean that it's going to be measured as a constant? Or what was that quote that Dollar likes to use, Stone?
Not a limit. It's a constant.
It's a
He
constant,
said it's a
not
constant,
a limit.
not a limit.
Right. Yeah.
Exactly.
Yep.
I
So
love
we
this.
come.
This is like particularly dastardly though, because right after this they go, not only is this how we'll give you the speed of light by giving you the properties of the vacuum itself, right? But we're going to remove the medium and then tell you that this perpetuates itself infinitely from nothing, and this is how it all works, right?
Infinitely from nothing.
Double dastardly.
Forever and always. Okay. All right, so next up we have a lesser talked about experiment. This is Martin Hoke in 1868, who used an interferometer configured in a way that it was half shielded. So in half of the shield was water, or I'm sorry, half of the shield was a tube filled with water. So what he was doing was basically he was testing the hypothesis that under Fresnel drag, where it was shown that the speed of the medium, imparts its velocity on the light. He was like, okay, if I set up my interferometer in a way that Earth's orbital velocity will impart on this stationary medium here, then we should be good to go. And at this point, they had started interpreting the experimental measurements that they can't find a V over C relationship anymore when they introduce a medium, because of the ergo situation, that really put a damper on things, because basically they had to come to the conclusion that for some reason the total velocity of Earth isn't imparted on the ether, and that's a really unsettling, ad hoc mechanism to keep your belief system in live. But at this point, they had come to the conclusion that if they got no fringe displacement, then that would mean that was proof that the Earth was in motion, because what that meant was that that Earth's motion was carrying the ether inside of the tube in the opposite direction, and that was canceling out the first order relationship. That was the explanations that they had to put forward to keep the Earth in motion, is like they had to introduce mechanisms that cancel out the first order effect. So that V over C relationship that we talked about earlier for stellar aberration, where it came out to where that angle ratio comes out to 30 kilometers a second, they never got that again with anything they tried in between here. There's some other things that I skipped, but I just kind of kept it to light and interferometry and the classics here. But they kept finding, null results to substantiate their position. And so by this time they were so backwards that them not getting a velocity shift here to the tune of what they predicted meant that the Earth was definitely in motion. So this is another one that will be referenced from Einstein, because the way that they've framed all this is that all these interferometry measurements that didn't produce a measurement are all going to be, predictions of relativity theory, because as it turns out, you can't use light to measure relative motion, because there's nothing for it to be relative to other than some other thing that's in motion. So with that, it becomes it gets into coordinate system transformations and invariance, which we'll get to as we continue. But this is the state of things in 1868. So Airy comes around in 1871, and he had heard that a guy named Plinkerfuse had put a turpentine-filled telescope on a zenith mount and measured a displacement that would correspond to Earth's velocity, meaning that the starlight coming into his telescope was slowed down by the turpentine, and Earth was able to physically move through space a longer distance before the light hit the eyepiece of the telescope due to the delay of the refractive index. and the angle was increased, and that angle increase is obviously going to be a ratio of the speed of light in that medium. So that would give them a that would indicate to them that the motion is real and not apparent. Apparent meaning just kinematic, meaning when you look up at the sky and see the stars moving, and everything moving around us, you could equally say that, we're also partaking in that motion. And it's equally valid to say that we're stationary and those things are moving around us. So, in order for the motion to be real, when you put water to a telescope like that, or any medium rather, the angle would have to increase. Unless if it doesn't increase, the implication would be that you are stationary and that the light already comes in with that drift. Otherwise, there would be an angle increase. So Aries has the boys whip up his own custom zenith mount over here, and he comes to the conclusion that when he adds water, that there is no appreciable change, and the aberration in air is the same as aberration in water. And a lot of people misinterpret this as proof that the earth is in motion. This isn't saying that. This is just reporting the experimental results. Airy isn't saying that uh, it doesn't come with the implication that the earth is also still in motion with it. He's just reporting the results, that they are unchanged. The implication could go two ways. It's left for you to interpret. um, but that is the interpretation. So if you could come up with some mechanism to explain why there's no change, then you could keep the belief system that the earth is in motion. Otherwise, the simple interpretation is that the earth is stationary and that the starlight already comes in at an angle. Let's see. Now, moving on to Michelson Morley, 1881 to 1887. What we're looking at here is this time, instead of looking for V over C now, we see that the equation is V squared over C squared. And now we're looking for a smaller order term, and he came to this squaring of velocity over c squared by geometry of the apparatus. So because the beam of light is going to be split perpendicular to itself such that it's going to make a cross, it's going to make you can think of it as it's going to make a there and back return trip. So because of that geometry, he was thinking that the first order effect that normally gets canceled out, there would be a little leftover effect on one of their return trips, based off of how you have the interferometer orientated with respect to the time at which Earth's orbital velocity is lined up with that. Uh, uh, is lined up with that when they would consider Earth's rotation being rotated into that velocity vector. So that's what all that's supposed to represent there. So he comes to this through Taylor series expansion. It's not V squared over C squared is mostly interpreted nowadays as a relativistic terms. It has like mutual exclusivity over, or it's like claimed mutual exclusivity over V squared over C squared. But as we're going through these, I'm telling you the principles on which they're squaring it, so that we can understand that it doesn't have anything to do with relativity per se, although it has been certainly rebranded, the V squared over C squared, as relativistic effects. But anyway, this was the purpose of the setup here. It was to detect a smaller order effect based off of a geometry that would allow for, if there's some mechanism mysteriously canceling out the first order effect, maybe this geometry would allow for a second order effect to bypass it and come through. So this is what they're looking at for. And of course, it comes down to 2 times the distance. So that's covering that round trip over the velocity squared over the velocity of light squared. And that gives them their prediction for how much the wavelength should change. So that tells them how much fringe displacement there should be, because there's a proportional ratio to the wavelength change and the fringe pattern, the fringe pattern is the destructive interference pattern that's caused by the waves overlapping. So So you can calculate all that ahead of time, measure your fringes, and then that'll be proportional to the wavelength change, which is also going to be proportional to the velocity that caused the wavelength change. As we learn through the history of Doppler and what have you, all these velocities have a specific change, which is all derivable based off of the V over C relationship, and V being the starting wavelength.
Can I challenge you to show us a quick view of figures 1 and 2 mentioned in the top right of this slide
Figures 1 and 2.
to see how A, B, A, C fit together and etc. If you got it, that would be cool.
Oh, you mean the old you mean this old thing, Stone?
I could
You
see it
mean
coming, but
you
no,
mean
no, I meant the PDF, I meant the paper, but
was
yeah,
that?
you keep going.
No, wait,
As you were.
wait. We'll get back to you. What were you talking
I
about?
know where you were going.
What were you talking about?
No, in the top right of this current slide, it mentions that when you're looking at the variable explanations, that big D is the distance of AB or AC in figure 1. So if we could see figure 1 and maybe figure 2, that would help people with interpreting these formulae.
Oh, gotcha. 11 meters.
It was a thought.
Yep. So would this help right here? Showing the
No, not really. No, but keep going.
okay. All right. So sorry, what did you want me to show?
The distance between AB or AC, figure 1.
Yeah, figure 1, which these formulae apply to, in the top right of this slide. You can see
You might not have
D,
it.
T, and T.
It's probably in the-
Oh,
reference that you have
in the
is-
paper.
I see what you're saying. I
In
see
the
what you're saying.
paper.
I got you.
In
I
the
got you.
paper.
I got you.
Cool.
I got you.
Figures. Just kidding. All right. I'll shut up now.
Gotcha. Okay. So let's see.
Yeah,
here.
now we're talking. Getting there. Is that figure 5? 4?
Which one are we looking for? Figure
1 and 3. We're looking for 2 and 1.
There we go.
Oh,
Start,
2 and
start
1.
with figure 1. That's 3. That's 3.
It's 2.
There's 2.
That's 2.
We're almost there.
Hey, orthogonal.
Oh, I guess that is it.
Ooh.
Actually, I
Why
think
does
that
it
was
say
1 and
2?
2 together there. Right
Oh,
there.
yeah, it
That's
is,
1
yeah.
and 2.
Yep.
Good shit. Okay, so we're just doing the triangle A to B to C. Cool.
Yep.
Yeah, this is about the splitting and stuff. Okay, great. Thanks, man.
Yep. No worries.
Good shit.
All right. Cool. So yeah, the premise is the light source starts here, hits a beam splitter, traverses the interferometer such that it makes the pattern that we just looked at over here, which is this. Has that nice there and back trip. We can see some patterns of it over here. And as it completes this, this is effectively increasing the length of the interferometer, the amount of reflections that goes back there and back. So you take that full distance. So you do 2 times that distance over the velocity squared over c squared, and that's going to give them how much wavelength should be changed if the Earth is moving through space at 30 kilometers a second. So we see here from their theoretical predicted pattern and wavelength change, it should have looked like this, and they measured just over 1 fringe displacement, which comes out when you ratio that out velocity wise. It comes out to be 6 to 7 kilometers a second versus the expected 30 kilometers a second. All right.
And why is that significant?
That's extremely significant because this was their last ditch effort to look for Earth's velocity in the second order, which was, they were out of first orders, which is hugely significant because if you can establish a first order relationship to something, then that's like a good kind of cause and effect, causation correlation kind of thing. You can kind of draw some heavier implication conclusions from that sort of relationship that are like more founded on experimental backing and reality versus now we're drifting off into like, okay, we don't have any evidence in the lab that we're moving. All we have is ratios in the sky, so it's significant in that regard, because it shows that no terrestrial measurement has ever substantiated the velocities that they assume and talk about in the sky.
So they have to assume 30 kilometers a second based off of the periodicity of the bodies in the sky, right?
Yep, based
Okay.
off of the periodicity of the sun, in particular for Earth. So to create the orbital period, for 365 days, that comes out to be 30 kilometers a second.
Right. So that's what they're expecting, because that's how fast Earth is supposedly orbiting around the sun, right?
That's what they need, not expecting, like pivotal, right? Doesn't move
Yeah.
forward without it, right?
Yeah.
And this fringe shift pattern, essentially, when you convert the wave, like frequent, like the amount of fringes, right, that equates to a velocity, right? They're expecting 30 kilometers, but instead their fringe shift shows 6 to 7.
Yep. Yeah. So you so so you
23
could
kilometer to second difference. That's nuts.
yeah. And as it will turn out, which we're not going to get into in this prezi, but Dayton Miller and Hector Manera, Yuri Galev all measured a sidereal periodicity, and then with this configuration of an interferometer, and then on top of that, all the other interferometers that are a closed loop, which is just adding another right angle to this to make the traditional SAGNEC closed loop. And when that they talk about, oh, we're measuring sidereal rotation, oh, we're measuring nutation and all this stuff. Well, all of those are the same measurements that these are producing, but they don't look at the relationship of squaring the distance between the fringes to get the velocity that produced it. They only look at it in terms of like um, uh, how was the how many times throughout the day did this distance increase or decrease? And when they take the minimum and maximums of that throughout the day and plot that on a sidereal timeline, they get their sine wave. So they look at it in terms of an angular displacement. So that's how they've separated the readings of
Wow.
the interferometer and made it appear as like one measures rotation, in particular ball rotation, and the other one measures nothing. The other one actually confirms relativity theory, because we know we're moving, yet this thing measures nothing. So that means that this
Game
theory,
over, dude.
that means that this theory that we have, that explains that is true, because otherwise
They
we'd be wrong.
eliminate transverse motion by taking a sampling of minimum and maximum only. Is that what you said? That's how they use that? What the hell?
Yeah, yeah. So when we talk about Mickelson, Gale, Pearson, at this point, the method of measuring the square of the fringes in terms of getting like a velocity, they completely abandoned that technology. Nobody knows it exists anymore, or whatever.
Oh, like the moon landing. Okay,
Yeah,
yeah, yeah, yeah.
yeah, and now they look at minimum max fluctuations over a periodicity. So in terms of like sidereal, when they do like ball rotate or whatever, that's what they plot the minimum maximums over as these fluctuate,
How does that translate to angular displacement?
because they plot it against sidereal time, which is a 360-degree rotation.
Oh, like in a, oh, okay, like on a circle. You just okay. That's crazy. So while this is measuring nothing, but it can only match this.
Right, right. And then so when Miller was measuring it with the configuration where they would interpret it with the squaring of the fringes to get a velocity component, when he's measuring that and the velocity doesn't like he's measuring that consistent sidereal and annual solar variation, so like on the equinoxes we get the biggest and smallest variations for the speed of
Yeah,
light,
that's what I was gonna
but
say.
but none of those correspond, or like but none of those come out to 30 kilometers a second. So they have to completely disown all of that, because otherwise, people are going to start asking, why doesn't how come you got your Mickelson Gale style ones and you're not measuring a velocity with that? where's
Yeah,
my velocity?
that was my huge disconnect. I was like, wait a second, how can you be plotting sine waves and corresponding with the sun when the motion corresponding with the sun totally destroys the entire purpose of what you're trying to prove? Like, hold on, what?
Yeah. So
So,
so that's
quick
why
question.
yeah, go ahead.
Sorry, I'm just trying to keep up. So they're measuring orbital velocity, but you just mentioned something about measuring the rotation of Earth. What was that?
So they measure a uh, sidereal fluctuation, and then on the yearly timeline that lines up on the equinoxes, the the speed of light reaches its fastest and slowest amounts.
Well, I mean, to be clear, we've got to distinguish between orbital velocity of Earth around the sun and sidereal rotation because that's important for what we're talking about. They're always trying to measure the orbital motion around the sun, and they always failed. No one's ever done it. All they've done is mistakenly measured the sidereal rotation, which they in Michelson-Morley mistakenly called Earth's orbital rotation, but that's why it was at such a small, 6 kilometers a second versus 30. Right. So
Right.
Yeah,
So
yes,
are,
and
are
and in addition to that, though, there the minimum maximum dimensions do occur on the equinox, so that does correspond to the annual solar time, but just not to the magnitude that they need for measurement. And then when they get into their interpretation with the closed loop, they don't even consider the annual solar at all.
okay.
And so if they were measuring ball rotate, they would measure a fluctuation that corresponds to a 24-hour timeline, but it doesn't. It corresponds to sidereal time, which is
Oh,
just
okay. Gotcha.
slightly less than uh, ball rotate time. Slightly less than 24 hours. I think it's, what is it, 23 hours, 56. Yeah. So
Gotcha.
slightly less, but that's the only, but mechanistically, right? They say that the sky moving is created by ball rotating. So the only way to interpret that measurement is through, okay, that must be a ball rotate.
Gotcha.
And they've got people so trained that, like,
yeah.
they don't even really think about it.
Any actual measurements of motion we're talking about interferometry or fringe pattern relationship is only ever measuring sidereal motion, which is real. Right? Sometimes they frame it as looking for Earth's orbital velocity, but that's never ever been measured. It's only ever measurements of sidereal rotation.
And if it's not the magnitude they expect, according to their math, they declared a null result.
Yeah. A no,
Yep.
dude,
Yep.
a null result. And not only that, on the backbone of Michelson Morley in particular, keep in mind, like I said, they measured just over one fringe, which corresponds to a velocity of 6 to 7 kilometers a second. When we get into relativity theory and the explanation put forward in terms of link contraction and time dilation, they have to completely ignore that magnitude of the measurement and say that a much, 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 much smaller effect occurred called link contraction. And that is actually what is why we can't measure any orbital velocity. And that's so crazy because what was actually measured is orders of magnitude larger than what they claim is the explanation as to why we can't measure it. And like they've got all these people rused into arguing that Michelson Morley didn't measure any difference in the speed of light, and we can look right at their measurement there. It didn't measure a null. Like, and then like they go on to talk about I didn't even include that, but anyway, their conclusion was that if the Earth is in motion, it must be moving slower for some reason. So to kind of move on from Michelson Morley now, we're going to talk about Voigt. We recently did a reading night on Voigt. Shout out to Stone. If I remember correctly, he carried all of the weight on that one. There was a lot of French in that one, if I remember, wasn't there?
We.
Oh, those little French, little Spanish, little German.
Yeah, a
Oh, mixed
little
bag in there.
mixed batch. It was a good time.
It's a fun little workout. Yeah.
but yeah, it was an awesome read on the history of void transformations. But now we're going to get directly into the source. So right here, I made available in the chat. I'll link it here again at the end. But anyway, we have the translated version of Voigt's 12-page paper on the Voight transformation. So this is the when you look into the history of relativity and the Lorentz transformation, you'll find that the Lorentz transformation is just the Voight transformation, and that's all it's ever been. So we're going to look at the principles on which this was derived, so we can understand what happened here, and we can compare it to how relativity says they derive its principles, and we'll see which one's more logically coherent in comparison. So here, Voigt starts us off with some differential equations that describe the speed of a wave in an elastic medium. And he's like, this is a well-known thing. So he whips that out to show us off the baseline. So this is going to be the wave is going to be propagating relative to this elastic medium. So the principles on the interactions of the wave mechanics are going to be all facilitated by the elasticity of this medium. So when we get into the compression of the wave, the retardation of the wave, etc., and all these quote unquote relativistic terms that are higher order V over C squared terms and half gamma terms, which is half of the V over C terms, half of the V squared over C terms. So when we get into these, we're going to see the source of them and where they all came from and how they were describing the change in oscillation rate of a wave relative to this medium, such that it could be described mathematically, where you could transform from different reference frames to see what the moving observer would measure the wave as relative to this elastic medium. So, and the math that they use here is going to be identical once we get through all this. But here around page 6, he derives the Lorentz transformation, which is the change in time and space. And what he's describing here with these higher order terms is the change in the oscillation rate of a wave, not the change of space itself or time itself in terms of like absolute time. It's the time of oscillation rate of the wave, how and then if the wave's in a medium, like how far could this wave have traveled based on that time, etc. So what these are is it's built-in functions that facilitate wave mechanics based on velocity. And what we're going to see here, this is the first Lorentz transformation. So this time term here is identical to a Lorentz transformation, and there's many papers on this, and some people try to argue that it's different if you divide it, not multiply. It's the inverse of it. These are all it's equivalent. They're all the same. So let's see, here was that one term. Oh yes, okay. So the big thing here, what we're looking at, the first time that time and space are mixed here, this is really important because Einstein does the same thing and Lorentz does the same thing, and this is what ends up being translated into the contraction of length and the dilation of time. So in the transformation, we have the original time coordinate is minus the velocity over the oscillation rate squared. So this is this represents the oscillation rate. So this is just the speed of light instead of we normally see it as c or whatever, but it's omega here. And then we have our gamma term, which is the higher order v over c squared term, and then there's even a half of this term that we'll look at later. But yeah, what this is describing is how the wave phase is going to change relative to the medium. It's not saying time is dependent now on position, making it separate from coordinate time, which breaks simultaneity, which is the foundation of relativity, where Einstein comes in and says, okay, relativity is actually simultaneity is actually relative, and time and space are relative, and they're functions of coordinate system transformations that are functions of velocity. So it's a completely physical interpretation if you remove the medium in which this was derived, because this isn't describing temporal or length contractions or anything like that. It's describing how a wave is going to change with respect to an elastic medium. And that's going to be really important when we look at Lamore's theory, when we get to the half gamma term, and we see that nothing predicted by Einstein's theory of relativity, so called, is anything new. This is all classic wave mechanics that has been disguised to not show c plus or minus v. Because what Voigt never says is that, this is a mixture of time and space. This is always in the context of wave oscillations and how they're going to change with respect to the medium. And then now we have Fitzgerald. So when you get into the minutia of link contraction and time dilation, it's sometimes referred to as Lorentz-Fitzgerald contraction, because they were hypothesizing, they were basically saying that the contraction, it would be of that this mechanism of waves compressing would also translate to material bodies compressing as a function of like the molecular structure that binds everything together, like the electrons in you and whatnot, would all be compressed, and that would actually lead to matter compressing. So they were hypothesizing that that would lead to, the actual apparatus contracting. So when you hear link contraction and time dilation in terms of the Michelson-Morley, where they talk about the apparatus contracted, well, what there's no official proposed mechanism in relativity, but classically what they were putting forward is that, possibly that the molecular structure would change based off of the square of their velocity through the elastic medium. And so we just got a quote here from Fitzgerald there talking about that. So we're seeing a slight change now from this being descriptive of how it's going to affect waves to now how this is going to affect material matter now. And then once Einstein comes through and removes the material medium from this, the physical meaning from it, it's going to become, just a mechanism of compression based on velocity with no actual mechanism ever described, but just that it happens. It doth occurreth or whatever. All right, so here we get into Lamore's theory here. And this is really interesting because he ends up with the half order gamma term. And again, he's deriving his everything under the principles of an elastic medium. And he gets into the same transformation here where the time and space coordinate are mixed. But again, he clarifies this is all about oscillation rates of a frequency and how it's going to change and how to keep it invariant under transformation. This doesn't, or so that you could analyze relative motion to the medium, not relative motion to another thing that's in motion relative to you, because there's no medium interconnecting anything. And the reason that you can't measure, that motion, said motion, is because it would be contracted by this much and dilated by this much. All of that's nonsense. All of these equations describe wave mechanics. Because all these exact terms we're looking at here are all going to be later recycled as relativistic terms that describe link contraction and time dilation of physical reality relative to the velocity of said observer.
So is it C plus V, or is it C always and everything is contracting as much as V would otherwise?
That, dude, it's so crazy. And then, so basically he ends up with this half order gamma term. So this is going to be really important because there's this thing called the transverse Doppler effect, which is supposed to be a mutually exclusive time dilation relativity prediction, where relativity is claimed to have a prediction that supersedes the classic. And while I was looking into this, like it was starting to look real convincing. They had a real nice one going for them. And then I found that our boy Lamar here, Stone helped me out. Larmore? That can't be right. Larmo?
I would guess. I mean, he could be American. Do you know where he's from? It could be just be Larmer. You know what I mean? But
Yeah,
Larmore,
I'm gonna go with a little more. That
something
sounds
in between
cool.
those two.
Yeah. So our boy here, who um uh comes up with this mechanism. So basically, the elastic medium of is going to cause retardation of the wave to this half order gamma function. So when we look at v squared over c squared, remember that's just the same as v over c, which is just the same as c plus or minus v, but this is just a higher order term. So this is, so you can think of this in terms of a much smaller effect, and then especially because it's half, that's going to be even smaller than the normal v over c. But nevertheless, he has deduced this, and this is going to be present in all wave mechanics. But there wasn't means of measuring this yet. So this is a prediction that he made, and this is going to be extremely important because there's going to be a transverse measurement that's made, and it's going to be to the exact tune of a half order gamma. Boys, it was a little concerning there, but turns out we owned it the whole time. So anyway, basically what this means is that a wave is always going to be retarded a little bit based off of the velocity of the emitter or receiver. All right. Oh, that broke my notes. Let's see. Let's try this.
That is some obsequious reality hidden in that math. They were just like, hey, you know what? Bump it up, all good.
That's moderately
Actually,
acceptable.
actually, time is not dilating, but the reality is warping at just the amount of it would have been if we added velocity to your c. It's crazy.
Yeah. Dude, the identical exact amount. Like, not even like, hey, bro, show me your new equation for your new theory. There's never been a new theory. It's always been this. There's no new equation. Show me your new equation for how the muon. There's no new equation. It's always been this.
Wow, some wizardry.
All right. And the reason that we
Dude,
the
it's
the
mine
reason
now.
the reason that the reason that they can't measure length contraction in reality is because there's nothing that's ever contracting physically. It's describing wave oscillations that are changing. When they talk about time dilation, that's always with respect to a frequency change. This is all it's ever been, always and forever.
That's pretty big.
It's such a weird position for them to try to argue from while simultaneously saying there's no medium whatsoever. It's not needed. Everything propagates itself, but also we need this medium to do this thing that we stole from it.
Oh, dude,
At
wait
the
till
same
okay.
time.
So the only saving grace would be okay. That's a cool story, Alan. You've got all this math that predates relativity that's exactly identical, derived under the principles of an elastic medium. Cool, that's great. But Einstein independently derived his theory of relativity based off of the constancy of C in all inertial frames. Okay, bet. We'll see how that plays out when we get to the derivations of everything to see if he actually independently derived it. Because if he didn't independently derive it, then we do own everything always and forever. Okay, so So to start us off here, Albert Einstein. So what I think happened is kind of like irrelevant to this presentation, but for the purposes of truncating it, let's just say all of this came from Einstein and there was no other influences, and this was just all Einstein's unique idea. So with his theory of relativity, time becomes relative. It becomes a function of velocity. So this gamma function here is the v squared over c squared, what we were looking at earlier from that exact identical how much a wave would change, or how much the wavefront would change for its oscillation rate. And here we have instead of it being an oscillation rate, this is going to be how much time changes on a graph when you when you do an XY graph. And then contraction here is going to be how much length changes based off of how fast you're moving. So again, we got that gamma. So instead of oscillation rates and waves changing, this is going to be physical reality now is supposed to change in accordance with these equations. So that's what he puts forward. So to prove his axioms, I'm kind of starting ahead of myself on the velocity composition. I should have started with the Lorentz transformation because he uses the Lorentz transformation to justify the velocity composition, which satisfies the law of parallelograms of velocities, he calls it, which is a really nice kinematic way of, it's like satisfying the laws of kinematics. You can show that your pluses and minus, like your me moving towards you or you moving towards me, are equivalent through the parallelogram of velocity law. But what we have is a velocity composition that instead of being c plus or minus v, now everything that gets added is going to be normalized by a term that at the bottom here, where's my oops, on this one, it's going to be normalized by this term at the bottom here, where it's 1 plus v times the two relative velocities over c squared. And what that's going to do is basically make it so that whenever you add a velocity to c, it's never going to exceed the speed of light. It's always going to be less. It's always going to be less than that. So what this creates is a Stone calls it the hockey stick. When you put it out on a graph, it makes a hockey stick. As you get faster, as the speeds increase, you get closer to the speed of light, the amount that it gets reduced by increases. So the same application here is what drives link contraction and time dilation, and what imposes the speed limit. And so when you start introducing these terms like this, it creates a quadratic function that basically creates that hockey stick effect. So when you increase your velocity, you get that sharp curve that makes it so that you can never exceed the speed of light. You'll just travel, parallel to it essentially, and never reach it. So this is what facilitates that mathematically. And because he was able to facilitate kinematic transformations off of that satisfy the parallelogram velocity comp, he was, very, very excited and enthusiastic for his theory, because if you can satisfy the kinematic laws, then you're good to move on to dynamics as long as you're not in violation. But as
The other part of the hockey stick is the unfalsifiability, because we just don't have the gamma as a species, to put it that way. That when you lay the hockey stick down and then the blade is upward to the right at the end of the graph when you're nearly approaching the speed of light, for the whole left 7/8 of the graph where you're nowhere near the speed of light, the effect is negligible. And that is what makes all of this almost entirely, and frankly, entirely unfalsifiable, because we simply cannot go that fast to see if links change according to gamma. You know what I mean? It's ridiculous.
That's so true. And he took the way that he interpreted that he was like doing all this correctly was he looked at the Fizeau experiment, where they measured the speed of light plus or minus the square of the refraction index of the medium. And he was like, oh, if the velocity isn't that high, like you were just saying, my hyperbolic curve doesn't do anything. It doesn't apply. And my formula just falls back to the classic C plus or minus V formula. So C plus or minus V here, and then then it's over 1 plus or minus V over C squared. Like that's that's absurd. So anyway, when you're not moving that fast, it doesn't even, like you said, it doesn't do anything. And then this equation just falls back to V plus C, V plus C. So he took that as like, oh, this must mean I'm extra super correct. And that's absurd, because of course your hyperbolic curve doesn't do anything at speeds that are non-relativistic. Like it doesn't, like the fact that the equation identical, like the fact that that's touted as like a surprising feature of the theory is insane, because why would you expect it to not do that? It doesn't, it's kind of mind-boggling once you
That's
Once you
crazy.
once you see it,
No,
Unverifiable and unfalsifiable.
yeah, when you actually do take the time, plug the numbers in, when you look at the difference between 30 kilometers per second and 300,000 kilometers per second, that's 30,000 to 1. 1/30,000th of the effect on a hyperbolic curve of efficacy. It's fucking zero. And that's all we're ever going to see while we're down here on the surface of Earth. You know what I mean?
oh, it's not coming out in the display very nicely, but this is just looking at
That's
that.
icky.
Yeah, it's just looking at that term again to show it up on the big screen. Just like that's what's driving the velocity addition to deviate from the classical Galilean velocity addition, where it would just be c plus or minus v. This is what drives this is what makes it so that c can never be exceeded, but you guys can't see it because it's all jumbled up in the thing, so sorry about that. But it was just this what we were looking at earlier here, just blown up. All right. So Einstein makes a lot of claims in his paper about in regards to this equation and how a moving clock should respond with a half order gamma, et cetera, for time dilation, and all of these things that will be later experimentally verified in confirmation of the theory. But as we learned, the direct actual equivalent is oscillations of a wave relative to a medium, and that could be the wave could be either slower or superluminal, measured superluminal based on whether or not the velocity is recessional or not. And so in 1913, one of the specific claims that Einstein makes is about how his equations apply to any closed polygonal circuit, even if it's in uniform rotation. And rotation is an extremely important concept in relativity theory because a lot of people will say that relativity theory doesn't apply to rotation, but we've done numerous presentations on how there's different ways that it does apply and they can get it to apply mathematically. uh, you know so it's like when they get down to a measurement that contradicts the theory, suddenly you can't take an integral, suddenly you can't suddenly there's no such thing as rapidity, suddenly there's no such thing as Thomas or Wagner precession, suddenly these things like don't apply to rotating frames. And it's, so they just like forget about all that. But it was specifically stated that Einstein's equations would apply in a uniformly rotating frame of any closed polygonal circuit. So DJ Sagnac over here comes up with a closed polygonal circuit where a light beam is split and there's no relative motion between the source and detector. They're both on the plate. They're fixed to the plate. The plate rotates, and there should be no relative motion between them two. The light beam should be split, and it should recombine clockwise and counterclockwise with no path length change. And that's what relativity theory would predict, unless there was something preserving the path link for there to be a timing difference, so that when these waves recombine, they're out of phase, and then they create a destructive interference pattern, which creates a fringe, which is proportional to the phase difference that was created by the velocity. So when we look at Sagnac's original derivation here for the Sagnac effect, this looks really messy and hard to interpret. But the important things that we need to know is that in his time, and the apparatus he was using in particular, they didn't have the ability to measure the actual wavelength, but there is like I said earlier, there is a proportional ratio to the fringe pattern to the change in the wavelength. So what we're looking at here is the wavelength changed measured as a fringe pattern, and that proportional ratio based off of the rotation rate of the apparatus and the length of the apparatus over the starting wavelength and the velocity of light. So basically, a classic c plus or minus v based on the rotation rate. And then you can kind of modernize that a little bit to get it to resemble the equation that we're all familiar with, which would be your delta t or delta t or delta phi here would be 4 pi times the distance times the angular rotation rate over the wavelength that you were using, and that's going to give you how much change there should be in that wavelength. So it's exactly identical. It's just written in a formalism that was uh, accounting for a different aspect of the proportional ratio that's measured. In modern equipment and all that, they can, they just use delta T4 times the area times omega over C. So in
They do a good
modern,
job of hiding C plus V, right? Because I can't tell that that's C plus V looking at it, to be honest.
well, it's just the same V over C ratio, and any V over C ratio, it's either going to be faster or slower. So it's either going to be an increase or a decrease on the ratio. So when they stack more stuff on top of it, all they're doing is like how the relative motion to that medium is going to affect the wavelength is like it's always the same thing. They just want you to look at it in terms of no physical medium, and for some reason this wavelength is changing due to relative motion alone. Let's see here. So anyway, the modern equipments and analysis, they typically use the higher order term too. So they use the C square too in their analysis, but to make it look extra relativistic and whatnot. But again, when at non-relativistic terms, that term would just fall off and it would just become the regular V over C ratio there. And then of course we have he's famous around these parts, Ruyong Wang, who measured the linear Sagnac effect. Now, this is supposed to be explicitly not something that's measurable because remember, relativistic velocity composition for inertial observers dictates that the speed of light is always going to be this measured as the speed of light measured by inertial observers is going to be dictated by a Lorentz transformation, which is going to change the coordinate system and the time rather than the wavefront. So what we would predict in reality is that you can't measure a phase difference of linear motion because the light is just going to traverse the changed path length and there's going to be no time difference because it's going to be contracted and dilated. So you're not going to see the change is what they would predict. Now, but what Wang measured here is the classic V over C relationship in the first order. What we're looking at here is a nice linear graph showing that motion at the nanometer scale. So that's really really important because what he was doing here, he did several configurations of this interferometer, but the most notable is the delta L here. So the parallelogram configuration that he came up with is that you start showing that the motion that the fringe produced is relative only to the portion of the interferometer that's actually moving. And you can derive that by having the interferometer configured in a way where only the top portion moves, and that's how he makes the parallelogram configuration. Apologies for not including that in the diagram here, but needless to say, if the motion was relative to the full loop of the detector, which corresponds to the detector, then you would have to use the full length of that, not the delta L, not the effective length, not the only part of it that's moving. So that's extremely significant because that shows that the movement is with respect to light in its inertial frame. It's respect to that. It's with the measurement is made with respect to absolute space. That's what's going on there in the measurement. So hugely significant. So we've got all these measurements that either line up with relativity and the classic predictions as a function of what they would call dilation, never the contraction part, but always wave, always in relation to the change in wave mechanics, disguised as V over C. Now, when they get to Doppler shift, they actually teach it and tell it to people like that the shift is like, it's an illusion, it's an apparent thing. We talked about that earlier at the beginning. But what we found out here through interferometry, through Sagnac and Wang, is that it's not an apparent effect. It's a real effect that causes a real fringe shift pattern that's proportional to the square of the velocity. And that fringe shift pattern that's created by the destructive interference created by the waves being out of phase proportional to the velocity that created the wave, that separation. It's just extremely important to understand that um, that mechanistically relativity predicts, if this is an apparent effect and that there's no preserving of path length of absolute space, and this motion isn't relative to absolute space, then they predict no fringe pattern. They predict that even if you're moving this loop or moving this segment of the loop relative to some stationary portion or some co-moving portion, because Wang did it such where the detector was on a air moving fiber or conveyor, so it was like using basically, it was just basically gliding on air, so it wouldn't have any resistance or drag when it was being pulled by the other section here. Their relativity would predict that those are inertial lads and that they're not producing anything that should be measurable. So the physical fringe pattern in reality is a direct contradiction to the theory. So this is why they have so much trouble with the Sagnac effect. This is the source of it. This is why there's so many different derivations for it, and why it's so convoluted, and why it has to be dressed up as like, oh, this is ultra proof of relativity theory, because it's the exact opposite. And especially moving at these velocities, because if this is proof of relativity theory, then where's the velocity for the Michelson-Morley experiment? Because when you get into relativistic velocities, you have to be moving at least 1% of the speed of light to get noticeable effects. And Earth moving at 30 kilometers a second, if you round the speed of light up to 30,000 kilometers a second, that comes out to 0.01% of the speed of light. So 30 kilometers a second isn't even fast enough for relativistic effects to even matter. Like the wavelength change that's produced by that is extremely tiny. Like I said earlier, what they measured is actually much larger than what they predict as the wavelength shift. So when Einstein talks about how his theory falls back to classical mechanics at slow velocities, well, one, mathematically, it's never even changed from classical theory at all, and it does. If your theory can't fall back to producing a physical fringe and then moving faster, it doesn't produce a physical fringe. That's absurd, because this is a first order relationship in the fringe, whereas relativity is only in the second order, right? Because that's um, how it was applied. It was applied to explain a second order experiment. They're assuming that first order effects don't even exist, and that they only need this theory to explain second order effects. So there should be no first order V over C fringe here. So the fact that there is another direct refutation of relativity theory, but they like to dress up the thing that falsifies their theory the most and pretend it is the thing that proves it the most extra bestus. So that's going to lead us to the Ives Stilwell experiment in 1938, which was supposed to be a test of the transverse Doppler effect, but it turns out that that's actually impossible to test because it's too hard, because the magnitude of the overlapping wave fronts that are coming at the detector before the angle is actually at 90 degrees is going to overshadow the lesser wavelength that's going to be produced at the 90 degree. So anyway, it's basically not possible to measure this transverse Doppler effect. And what the transverse Doppler effect is it's the suppose you have a detector stationary, and then you have 90 degrees to that detector. There's an emitter moving parallel to you. So as that emitter changes in angle as it goes across, above you, as it crosses your zenith. You can think about it like that. As it comes to your zenith, there's predicted to be no Doppler shift because there's no path length change between you and the emitter at that time. So the classic theory, if there's no medium, would predict that there's I'm sorry, the classic theory, if there's a medium, would predict that there is a Doppler shift. But the way that things have been reframed is that the classic theory doesn't predict a shift, and only relativity predicts a shift, and it's to the tune of that half order gamma that we looked at earlier, and it's only as a function of time dilation. So this gets really interesting because now we have, the way that it's framed is that we have this mutually exclusive effect that could be tested that could separate classical from relativistic physics. And this experiment was done in 1938 by Herbert Ives, and through a series of trial and error, he determined that it wasn't really possible to do the transverse like I talked about earlier, because having that perfect angle line up and then deciphering it out of all the other possible measurements, leading up to that is it just doesn't work. So what he came up with here was a canal to shoot out a ray that gets reflected during the process of reionizing an atom. So they take hydrogen gas, they strip it of any ionization, they make it neutral, they send it through an electric field to accelerate it, and then they ionize it again, so it can go through this electric field without having its charge affected. So they send it through, neutrals essentially. It gets accelerated through this electric field, and then they ionize it again on the other end of that, and the reionization of that emits photons. It emits light, it emits radiation. So in that, they now have the ability to measure based off of a reflection mirror. They can measure the longitudinal Doppler shift for recession and approaching. So they can measure blue shift and red shift from something that's moving at an extremely high velocity. Now they can't get that perfect 90-degree or set up, but having something that's moving close to 1,000,000 kilometers a second in some of these cases is close enough to distinguish some of these relativistic effects. So we're going to look at the apparatus here and go over the measurements here at the end, and then we'll recap on the math used to describe the effects and what this gentleman was actually proposing. So earlier we went over that gamma order term, which is that half gamma term, which is 1/2 times the velocity squared over c squared, which is a really small amount. And that actually traced back to Lamore's theory, where he was saying that all motion is going to cause a slight retardation to that half order. So Ives was actually testing that effect, but because the equations are identical to relativity theory, they actually co-opted these measurements as proof of relativity in the transverse Doppler effect, even though no transverse Doppler has been measured on either side, and it was just the longitudinal, which there would still be a time dilation effect for them, but it's derived under the principles that it's just going to be retardation of a wave based off of motion relative to a medium. So here we have high order confirmation of what Lamore predicted in the 1800s versus what Einstein put forward as completely independent of physical reality. I'm sorry, independent of a medium, sorry. So here again, we can look at the apparatus now, and it has a mirror on it. So if the reionized hydrogen atom is moving this way, it hits a photon, it hits a mirror. Going this way, it's going to be reflected back to another mirror that's going to hit a spectrograph. This is just a truncated version of the route that it's going to take after it gets reflected. But anyway, we can see here that this is going to be blue shifting and red shifting. So we can see the the difference there, and then each one of these blue shifts and red shifts corresponding to the um, to the to the ionization of the hydrogen atom is going to, that's going to be produce the photon, or that's going to produce the wavelength or whatever. So that wavelength is either going to have a small change in this amount of energy to the tune of that half order gamma, or it's not. And that's and this is what he was testing. So is it going to be oscillating a little slower, or due to the motion of this hydrogen atom, or is it going to be or is there going to be no change? What's going to happen? So here's just another diagram showing that same situation here. So light that goes this way is going to be directly going into it. That's going to give us blue shift. Light that hits the mirror and comes back is going to give us the red shift. So it's a really cool configuration here. And here is the top overview that we're looking at. So the canal is posted over here. We have the mirrors that it's going to hit for diffraction gratings that it's going to bounce back off of, so that it gets a photo, so that it hits the photographic plate over here, where they're going to take their spectrograph measurements, and those energy changes in the spectrograph are going to dictate the wavelength change. So they're going to be directly measuring the wavelength change as a function of the color change, or rather the displacement lines, where there should be color. So anyway, here's a nice black and white of the full apparatus there in the lab. This is by the standards of black and white pictures that we've looked at for basement equipment shown to us. This is by far the most well lit picture that we have of equipment. So shout out to the boys who took that. So here we have the results. We have this observed shift here. We have this small order term here. Now this is done in the angstrom units. So this is 10 times smaller than a nanometer on the wavelengths. And this small difference here is that gamma order term every time. I made a spreadsheet to kind of go over this and see what the differences were between some various formulas that I found that said that they predicted, the classic theory for saying that they predicted the same exact shift and whatnot. So I put those formulas to the test. And in terms of angle, when the angle is actually 90 degrees, there was one formula that did match a prediction for relativity. It was a pretty close one. But that was like, an angle specific one that didn't even apply to this scenario. So it's not applicable for the longitudinal one. And I couldn't get any longitudinal matches for that half order gamma term. I could get the most I could get off was being off by half of that gamma for the regular V over C. But then that's when I found the, going back through the history of things, I found that the original source of the half order gamma term is just the term that was put in from Lamore, that was derived from the principles of waves being compressed by an elastic medium. As you move through it, there's going to be retardation that's proportional to that velocity, and that's exactly what was measured to an insane degree. So we have different hydrogen levels here. We have hydrogen 3, 2, and 1, so that it corresponds to like different wavelengths, different velocities that they would interpret for how they're deriving this. So we have this corresponding to different wavelengths and different velocities to a high order of, to this exact, guys, it came out exactly. It was pretty crazy. Unfortunately, I destroyed the calculator in a calculating incident where I was trying out different things, and the calculator no longer resembles anything useful. So I'll be remaking
I've
it.
got that file if you want it.
Dude, do you have the original?
I pulled it when you posted it.
Nice.
Want it?
Yes.
Let me telegram it to you real quick.
Yes. That'll give me a good baseline.
I
That'll
thought you were
be
making a moon landing joke. You actually have some data that you guys calculate on the fly that you then thought was lost that someone preserved. This is exciting.
So it's not preserved in the sense that it's going to be useful. So what is this? Oh, this is from something else.
There you go. Check Telegram. That's your spreadsheet, your TDE calculator.
Thank
That's the
you,
stuff you're talking about,
sir.
right?
ODS, yes. Copy.
To the rescue.
Well, unfortunately, it's not going to be
I've actually
This-
trimmed it up a little bit.
the super rescue.
You're gonna have to open Excel and Linux real quick on the fly in front of everyone.
Oh, Jesus. Let's see. No, this is in full bastardization form.
Oh, this is post edit.
Yeah. Yeah. But what was
I
coming
see.
up here in this? How do I don't know how to even make this not look. Hang on. 1 second. Let me just pull it up real quick. Whatever, Shane. All right. So we'll look at it right here real quick.
Yeah,
Set
that's
a cough.
So this turn, let's see, what was it? Nope. Where was my gamma? Where's my half order gamma? There we go, this one. So this half order gamma term right here, when I would input the relative wavelengths for everything, like I'm going to change this up and make it so that you can, like it'll have a drop down menu like the other stuff that'll correspond to the right wavelengths per the data table and all that. But anyway, what kept coming up was the gamma amount was what he measured. So as I would change the wavelengths and velocities of each one of the things, it would correspond to what was actually measured. And it was really cool to go through that process and see what was measured. So to a high degree of accuracy, that the amount of retardation that is experienced by an emitter moving at quote unquote relativistic speeds was measured. Unfortunately, it has nothing to do with time dilation, and it's it falls under the orders of Aether. Oh, and then real quick on, let me see. I know a big part of this was, did Einstein independently derive the
He had help from his husband.
no, no, not only that, but did he independently derive relativity theory independent of any ether mechanisms? So let's take a look at that real quick. Let me see where I misplaced those. Would it be in here? Nope. 1 second. Oh, that's so crazy. Where did I put those? I put them in the wrong spot. That's what happened. The issue was me. All right, so earlier I gave a big shout out to It's BS on YouTube and Twitter. So I'm going to be using some of his diagrams and what he's been arguing for a number of months now and showing this repetitively is the equivalence and the equations for the transformations, and not only that, but the principles on which they were derived. But let me see if I can, am I able to present this one too, or is it going to be messed up? No, it's going to be all messed up. All right, we'll just have to look at it like this. But anyway, what he points out here is that Einstein's postulates are, the velocity of light is supposed to be independent of the state of motion of an emitting body. And he goes on to derive how the speed of light works as this half order term, basically splitting the speed of light between a moving detector and a stationary, reference frame. So he didn't derive it independent of the state of motion. He used the state of motion to support the assertion of his postulate because it requires the relative motion between them to have a symmetrical midpoint to do this half order term to basically make the one-way speed of light the speed of light, so that when it bounces, so that when it completes the trip, it's the same speed. They often talk about, the two-way speed of light, my two-way speed. We only have a two-way speed. Well, that's based on the math principles that Einstein puts forward, and it leaves ambiguity for the one-way speed. But in order for the one-way speed to work, I'm sorry, in order for his theory to work, the one-way speed has to match the two-way speed. So it's an assumptive thing, but he's using relative velocity to show that, and it's showing that the velocity of c isn't independent of a state of motion. So he failed to independently derive his Lorentz transformation of an etherless theory. So everything defaults to me, or it defaults to us. Sorry.
Yeah, that sounds like par for the course for a mainstream method.
Alan,
Yeah.
why is it every time you present tiny math, you have to do so on 1/3 of your screen in a full screen environment? Like, is it impossible for you to use 100% of your screen just one time for me? Oh my God, thank you. Oh, that's so easy.
Hey,
Oh,
look.
thank you.
Dude.
There's superscript on some of these. Look at that. Hey, X
Oh
prime.
my God, it's legible and
Oh,
everything.
shit.
Oh, that's so much better. Like, I'm trying to read all this, and if I can't do it, and my face is 2 inches from my screen.
All right. Fair enough. All right. So the basic issue here, right, is he's using the relative velocity and the two-way speed of light, and then having it so that the one-way speed is equal to the two-way speed to make his assertion, and he's not independently deriving it of a state of motion. So, and then but the fact that this is relevant to a rest frame, which he is considering, oh, this observer is just stationary. We can consider an observer moving at a uniform constant velocity as being equivalent to stationary. Well, you know what you can also consider stationary? Absolute space, the lab frame, etc. So Aether, some sort of mechanism like that. So we'll just go ahead and swoop all that back up, and we own all of it. So any accolades that are attributed to the correctness of relativity theory, we own all of them. And
I like
it's
how they
just
have to they have to use like the wave equation and then pretend that also it's not a wave and a simultaneous infinite amount of BBs that pass through a non-medium while using the formula for a medium in a wave. I like that they have to do that, because there is no alternative, because that's where everything comes from.
yeah, pretty crazy.
Imagine pretending there's no energetic medium and then using the properties of that medium to justify the constant that which defines your whole reality. Like, that's a hell of a position to defend.
Yeah, dude, it's like you never want to see your boys take a bad position, and it's like this is one of the worst possible ones you could ever take. We have like on documented record all the math that predates relativity coming through with the identical math. Like the thing is like they have no ability now to differentiate between to be like, oh no, this is link contraction and dilation. Like, no, it's just C plus or minus V. And then let me show one other thing that I missed real quick.
We're just hitting 2 hours right about now.
Yep, I'm just finding this one last thing, and then I should be good to go. Should be good to wrap. If anyone has any questions or comments in the meantime, though.
I just want to say great, Prezi. That was, I mean, a lot of it's over my head, I'm going to be honest, but I'm, just keeping up, and there's some really good nuggets in there. I mean, just how general relativity is, it's classical theory. It's pulled from the classics. I mean, there's so many good nuggets in there.
Yep, it's never not been classic. And the fact that they say that it falls back to classic, it's like, okay, well, it can't fall back to a pretend V over C and then a relativistic V over C is fake. Like it's just always that, and it's just never described reality. It describes the oscillation rate of a wave relative to a medium.
Right. It's all interpretation of the measuring the oscillation, the fringe shift. It's all waves and mediums and their interpretation of it.
I do think it was beneficial to like high timeline it like that to go through of how actually it's always been C plus V, C plus or minus V, and then how it was guised as something else, how it was misinterpreted, then how it was hidden, and then how it was never spoken of again, even though everything that they do is based on it. I think that it was important to elucidate.
Yep. No, thank you. And I thought so too. It was like as I was going through this, like, dude, this presentation started as something slightly different, and it led down all these different rabbit holes of things that I had been like putting off to look into in relativity, like the transverse Doppler, uh, some of the aspects of the velocity comp, the Voigt transformation, and then it all just came to a head, like Lorentz's ether theory, Lamore's theory, and then all of these things came to a head because all the math turned out to be the same, and then it's all rooted back in this right here, which stems from Voigt's paper, where he does this time transformation where he says t prime is equal to t minus velocity times the x coordinate, distance over the over v squared. And so what this does is, the relativistic interpretation is that time is now dependent on velocity over c squared. Right. So this is where they're like, oh, time and distance are a function of velocity. They're no longer fixed values. And this is just done for ease of transformation. This transformation is entirely equivalent, and it doesn't include the time term again. But the fact that the time term is in this one, like, it's mathematically correct, but the physical interpretation that comes out of it can be misleading if you don't clarify that this describes oscillation rate of like a frequency change of a wave relative to a medium, not a change in literal temporal time in terms of this.
Well, listen, you gotta
It's
prove to
Doppler,
me.
dude.
You gotta prove to me that that's not actually the rate at which the universe warps and rotates, so that my Lorentz contraction makes physical sense. Okay.
Indubitably.
Oh, look! If I could only have seen all of your slides up close like that, I would have known what you. I'm just kidding.
Dude, was it that bad for each of them?
It's bad for me personally, but I might be
Well,
super biased.
my monitor is gigantic, so do your worst. I'm still going to see it.
Nice. All right, cool. All right, Cass, are you there? I was hoping you would have some relativity
him there.
inputs.
Stop your grinning and drop your linen.
I think I had a different version of that one.
Says you're unmuted, but we can't hear you, Cass.
When's the last time we actually heard Cassander? It's been a while. Is this mic set up?
It's been a
Yeah,
while
couple of months.
since I could, or whatever. Stone, help me out there on the vocals.
It's been a while since you showed light my way. Yeah, it's been a while since you made your case and play. Yeah. Nope, needs more time than that just to find his mic. Unless he's not even in the room. Who knows?
No, he came off mute, but I don't think his mic's working.
I believe that this technological hurdle will be overcome in a timely manner.
He'll get it.
Hopefully not a time-dilated manner.
Oh, that would be the worst
Although-
possible scenario.
It's actually just going to be adjusted by my velocity depending on if you go east or west, but don't tell anybody that.
Should we also advise him to maybe leave and rejoin Mount Wilson to see if that resets things?
We could try, but we could
Wouldn't
also have Lily do a coffee read in the
Yeah,
meantime
our ambassador is
to exit
here.
us out. Lily, you were saying earlier that before you started drinking brushtail coffee, that you really didn't have any understanding of physics and that you were kind of like, deaf, dumb, and blind, so to speak, and that through just drinking brushtail coffee, you absorbed all of the information that comes out of ether cause through osmosis, essentially. Am I understanding that correctly?
Yeah, maybe because our beautiful brushtail owner is a flat earther with us, so maybe his flat earth physics vibes got in there because he hand roasts all the lovely coffee, so tasty. You know what I mean?
Oh, I do know what you mean. And flat Earth vibes are awesome.
Yeah,
They
it's the very first side effect that I experienced from drinking brushtail coffee. I was like, oh my God, I can understand physics now. Woo! Hey, having said all that, I just want to say that you guys are the gems of the real science, physics, flat earth world. And it's just so marvelous. Just thank you so much for, keeping it going week after week, putting out all that content and hard work. And I try to shill for you every week to get people to subscribe to your account. So thank you and love you guys. And hopefully
you,
we'll, never mind, bye.
Thank you so much, Lily. Your contractually obligated shilling is very fulfilling. You're fulfilling your contract and contractual duties to the utmost. It's really, your work ethic is astounding.
Thank you.
We appear to have lost Cass, so I'm going to go ahead and wrap up for the night. If he ends up rejoining us and he has some afterthoughts on the Prezi or whatever, I'll record those and upload them to the YouTubes later, and we can enjoy a little after party or something like that. But with that said, thanks everyone for tuning in. We're gonna wrap up for this week. We will be back on Friday for Twitter community night. See what the lads are doing on Twitter. I'm sure the relativistic lads will have a lot to say. Maybe some of the relativity lads will show up this Friday, and we can have a nice discussion about C plus or minus V and or the contraction and dilation of temporal reality. And Sunday we'll be back on Globebusters where I will be presenting this. I think is it my turn in the rotation now? I think it's my turn.
It is? Okay.
I think so. I'll be presenting this, and then next week will be the Stone of Men. Hey,
Yeah, we should talk about that.
we will. We will. All righty. See you guys